The talk will be essentially application-driven, meaning that I will present results that initially were triggered by a question in air traffic control and, in fact, automated air traffic control. So briefly, what is the problem and what people are trying to implement in future air traffic systems? So first of all, right now, when you want to fly from one origin to one destination, if possible, you want to fly straight lines or perhaps geodesics if you want to fly on a sphere or perhaps an ellipsoid. And of course, if everybody wants to do the same, you will have crossing points and perhaps conflicts. So conflicts is something that means that you are getting too close to each other at a given point. So right now, you have guys in charge of this. Here is the microphone. You have guys in charge of organizing the traffic in such a way that conflicts will never occur. In fact, they will occur with a very, very small probability, and it's very bad for the guy in charge of the traffic at that time. So they are instructing planes to divert the routes in order to avoid each other. So this is a standard maneuver. It's known as the offset maneuver. It works for a human-centric system, meaning that in a human-centric system, most of the time, you will fly straight lines, and in fact, the traffic is organized in such a way that you know where the aircraft is coming, meaning that even if the route is more complicated, it is made of points and straight lines. This is the point. This is what is important. But unfortunately, the traffic is growing. It's bad for perhaps pollutant emission, but it's a fact. And it is a projection, it's not, perhaps not true, but people expect the traffic to have doubled by 2050. So it's quite an increasing, major increasing in traffic. The problem is that if you keep using ATC controllers as the sole mean of organizing the traffic, the system will break because they will be in charge of too much aircraft at the same time. So the idea is to introduce some kind of automation in the system. But you need to keep the human in the loop because you want the people boarding the planes be confident in the system. So you keep some safety net, meaning that you have a human being able to recover a situation produced by a machine. So this is the point here. Humans will always be in the loop. It means that if an automated system produces a planning, then the planning must be usable by a human operator. So it means that you cannot produce planning that are too far from the current airspace organization in airways, meaning points and straight lines connecting the points. So the big issue, in fact, with automated systems is that right now they are producing plans that are not usable by a human operator. So the question is, can we take an automated system producing a planning and put in the system some ways of having at the end a planning that is close to what the people right now are used to control. And in fact, it was the purpose of the work. So the idea is to start with a solution proposed by an automated system, then correct the solution in order to recover a root system. So, how to do that? You know that we need to be close to straight lines, and furthermore, we need to be close to something that looks like a graph, meaning that we want to have merging points, meaning that at some point I will merge two flows, and perhaps branch points, meaning that at some point I will divert the two flows in order to have the aircraft reaching the destination. So basically, how to put in the design of a path planning a knowledge about I want to end up with something looking like this scheme of airspace organization. Okay? That's the point. So the idea was to say that finally, if I look at entropy, entropy will perform the task. Why? Because if I imagine that a route is some kind of very well concentrated probability or density of presence at some point, then if I look at the curve minimizing the associated entropy, I will have something that is a straight line. It's not so obvious, but it is how it works. So I will explain, in fact, how to do that and what are the results. So first of all, how to turn a curve or a system of curves into a probability density. The first idea is to compute using a grid and some kind of histogram, meaning that if I have a route going through the cells of the histogram, I will just compute, if I have sampled positions, how many points are falling in each bin, and I will sum. Okay? So I sample from time to time. I simply say that the probability of presence, or perhaps the spatial density, is just the number of occurrence of samples in each bin, and then I divide in order to normalize. The problem is that if you do that, it's not working. All the people are doing that way, but it's not working. It's not working because if your aircraft is slowing down, you will have more and more samples, meaning that you will overestimate the cells where the aircraft has low velocity. So the idea is to compute not the number of samples falling within the cell, but in fact the length of the curve falling within the cell. And if you do that, you will end up with something that is insensitive to a change of parametrization in the time coordinate. Okay? It will be geometric. Of course, in practice, we want to use kernel estimates instead of histograms. So the idea is to define the density this way, meaning that you take a kernel. So here is a radial kernel. It is dependent on the norm of the distance between the point where you compute the density and the position of aircraft I at time t. You multiply by the norm of the velocity. This is in order to get something that is invariant under reparametrization. So it will be something that is related to the length. And of course, you take the integral from 0 to 1 and you sum over all the curves. This is, in fact, an invariant mean of defining a spatial density or probability of presence density for a system of curves. It turns out that it has a nice interpretation. If you imagine that the trajectory is, in fact, can be represented as a current, a direct current, then it is here a regularized version of the direct current. Of course, most of the time, you will be dealing with normalized kernels, meaning that you want to have a unit integral of the kernel on the domain. In such a case, you can check very easily that the denominator boils down to the sum of the length of the curves. So we will select only normalized kernels. The entropy can be computed using the density, the approximate density, just by the standard formula of the sum of d of x log of d of x. So this is the value we want to minimize for the curves. Okay? You can check easily also that if you start with a single curve and some basic assumptions on the kernel, you will end up with a straight line. So now, how to compute the variation of the entropy with respect to a curve? So it's not very difficult to pick up a curve and consider a vector field along the curve and pretend it is a variation of the curve. And doing that, you can express the derivative with respect to curve J here as applied to epsilon. Epsilon, in fact, is the vector field here. And so you end up with an expression. So you can see here that due to the fact that detailed, in fact, is a density, there is no derivative with respect to the second part, because you can check that you will integrate the variation of the density, and in fact, since the integral of the density is 1 all the time, you will end up with 0. So the remaining term is only the log times the derivative of the density with respect to the curve. So if you remember well, we have a numerator, we have a denominator that is just the sum of the lengths. It's clear that you can compute very easily the derivative of the denominator. It is a standard computation. And you end up with the fact that the first order variation involves only the normal component. And in fact, you recover a very well-known fact that in fact it is proportional to the curvature. So it is just a curvature displacement. As usual, since you have a gamma prime of t in the expression of the integral, it is invariant under reparametrization, meaning that the only displacement fields that are to be considered are normal to the curve, because you can absorb, in fact, the tangential component into the reparametrization. So the denominator is something very easy to compute and to understand. For the numerator, you can compute pretty much the same way. You will end up with a normal component. All the time you will end up with normal components. The first part is related to the derivative of the kernel. It's not so surprising. And the second part is relative, once again, to the curvature term. But this time you have a weight given by the kernel. So what is interesting right now is to try to have an interpretation of, sorry, I will take such an example. We will have an interpretation of what happens when we try to minimize the entropy. So the displacement field is given by the equations here. In fact, you can even remove the epsilon in order to have something that is easier to understand. So it is only a normal component. So it is the displacement field, but only for normal component, because remember the tangential one is absorbed in reparametrization. And if you look at the terms, you can safely forget about the sum of the lengths, because it is something that is a multiplicative constant. You see that all the time you have a log occurring as a weight in the expression. And this is very important. Why? Because when you minimize the entropy and you look at the moves here, you see that due to the log, the important points are the points where the density is going to 0, because the log will diverge. and it will induce high displacement. Okay? It is completely different from a procedure that uses, in fact, the density and tends to aggregate the curves on areas of high density. Here, you are repelling curves from areas of low density. So it is something quite different, meaning that the voids in the system will tend to push the curves together. Okay? So here in such a case, you have a void here, and a small here, but you will push the curves due to the voids and not due to the fact that you will increase the density. So this is really the important point. The important point is when you minimize the entropy of a system of curve, you will repel the curves from the voids and not too much attract from the areas of high density. So the question is now, from the expression here that is quite complicated, but not that much, but anyway, it has to be computed. Is it possible to implement the displacement field? Meaning that in practice, can we really compute the displacement due to an entropy minimization of a system of curves? So to do that, here we have implemented something very, very simple. So it is not sophisticated at all. It is just a landmark-based procedure, meaning that we consider on curves landmarks, and we move only the landmarks according to the displacement field computed. So it is interesting because, first of all, if we want to implement on a computer the previous, not algorithm, but criterion, then in fact you are working on an infinite dimensional space that is a manifold. It is the quotient of the immersion from 0, 1 to R cubed by the group of orientation preserving diffeomorphism from 0, 1 to itself. So it is normally not possible to implement such thing. But anyway, using the landmark approach, so it is very simple. You just move the landmarks and compute, in fact, all the quantities related to curvature and something like that using the landmark approximation. If you do that, you can compute in reasonable time, meaning that for a system of about 10 curves, the time needed is about 1 second on a laptop. So it is quite fast. And it is fast due to the fact that the kernel that was selected was compactly supported, so we can compute the density using a trick, a computational trick, meaning that we compute on the GPU and not on the CPU. So it's quite fast, meaning that it can be used in real time. And so this is the result. On the left, you have a conflicting set of trajectories, meaning that everybody are crossing at a given point, and we are paying attention only to things that occurs in the disk. We will not move anything outside of the disk. Here you see that after applying first the automated system, so it produces a result that is absolutely awful for a human because it tries to make aircraft in a roundabout. If you put the entropy criterion within the system, you end up with something that is quite similar to what a human controller will do, meaning that you have a merging point, then you have a branching point. Okay? So it means that at the end, you have a system that produces in an automatic way things that can be used by a human operator. So right now, it is used. It is used for research. Of course, it is not used in operational setting. So it is used for research, but it works, meaning that we have an automated system using the entropy criterion for the curves produced, and it turns out that the planning produced are usable by a human operator. So this is a good point. Problem is that it's quite, so I tell you that for 10 trajectories about 1 second, but unfortunately it's not scaling well, meaning that if you consider, for example, 100 trajectory, it will be several minutes, perhaps 10 minutes and something like that. So currently people are trying to port the algorithm to GPU only, no longer using CPU. So it is a work in progress. We hope to complete it by the end, perhaps, of the year, this year. And second, the problem is that the algorithm is not taking the fact that is not taking into account the fact that if two routes are close one to each other but in opposite directions, normally you will not suppose to make the curves move one to the other. But right now it is what happens, meaning that in such a configuration the curves will tend to merge. We have an improved version of the algorithm that uses, in fact, a model of the curves with values in a Lie group that allows to take into account the headings. Unfortunately, the computational time is really prohibitive this time. Okay, this is the end.
Thank you very much. Let's thank the speaker, please. So, yes.
Maybe I can shout.
Wait.
Yeah, it works.
So, if you go back to the picture you showed toward the end with the different paths.
This one?
Yeah, thank you. So, how should I read this? How many aircrafts are in that picture? Is it 5?
No. In fact, it is the number of the routes are converging, but there are 15 aircraft.
15?
15, yeah. It's not, in fact, here you have just the routes, and the part that is plotted here is just to show one of the aircraft in the sector. But on the routes, when the planning is done, you have aircraft coming on the routes through time. Okay? This is a snapshot.
Okay.
Okay? When you want to plan here, it is, say, not a real tactical planning, meaning that it's not a real conflict avoidance system. It is a way of organizing the airways in such a way that conflicts occur only scarcely.
Okay.
Okay?
Okay.
So, in fact, the complete simulation is 15 aircraft. This is a snapshot.
Okay.
Okay? But this is the route network produced at the end.
Thank you.
Yes.
I would like to understand a little more specifically why you use the entropy. I mean, you gave some explanation, but let me ask you. So, the entropy you use on the mass,
Yeah.
do they all function as kind of entropy dispersion? Or either explanation with kind of mass radiation?
No, it is. No, it's not related to large deviation principle. It is really to occupation, to spatial density. Okay, so it means that, in fact, perhaps the best way to have a look at the behavior of the entropy is just looking at a single path. Okay, if you look at a single path. Imagine, for example, you want to attract curves to the areas of higher density. Okay? It is the way people are doing bundling of curves in visual analytics right now. Okay? If you have a single curve, then the density is located on the curve itself, and nothing will change. Okay? Unless, of course, you have some regularization, meaning that you have a kernel applied along the curve, and in fact, you will have an overlap of the, for example, in such a case, if you have an overlap of the kernel and you attract towards the highest density, then you will have a shrink of the branches, okay? But for entropy, it's completely different, because if you look at such a case, it is less concentrated than a straight line. So the entropy criterion will tend to produce straight lines if you start with a single path. And it is completely different from the case of density bundling.
Any more questions? Yes.
So it's not fair. It's not fair. It's the co-worker, the co-writer of the paper.
So in the implementation, how many landmarks do you need, and how do you choose them, these landmarks?
It's a good question. So very simple. For the landmarks, you select evenly spaced landmarks. Okay, you compute the arc length, and you say if you want 10 landmarks, it will be evenly spaced, meaning that the distance between landmarks using the arc length is the same. Okay, the number of landmarks, it's a good question, because the implementation here was not made by me. I will say around 10 to 20, approximately.
If there aren't any more questions, I may have one myself, actually. So you were interested in minimizing entropy for reasons which you explained, but wouldn't you also want to minimize time or cost of travel, and can that be integrated into your algorithm?
No, it's completely different, meaning that if you want to optimize the trajectory with respect to a criterion like the cost, or perhaps the time, or the fuel consumption, whatever you want, you need to ensure at the same time that flights are avoiding each other. Okay, so first of all, it is complicated. Second, the trajectory produced are complicated, meaning that they are not, most of the time, a human operator is not able to control the traffic produced by an optimal planner. So in fact, the trick is to use an optimal planner, but to correct the criterion using the entropy.